In this lecture, we're going to go over the directionality of a process and then extend that to the energy balance for open systems. So if we consider an isolated system that consists of a system and portions of the surroundings, we have their total change in energy equals 0 because the system is isolated and no energy transfer can take place across the boundary. Since energy is an extensive property, we can break this up into E of the system plus E of the surroundings equals 0. Then we can also do an entropy balance, which reduce down to our change in entropy is equal to our integral plus our entropy produced. And again, there's no heat transfer, so our change in entropy has to be equal to our entropy produced for our isolated. So our change in entropy has to be equal to our entropy produced for our isolated system. As entropy is produced in all actual process, the only process that can occur for which the entropy of the isolated system increases. This is why we say entropy always increases. Since entropy is also an extensive property, we can break it down into the change in entropy for the system plus the change in entropy for the surroundings is equal to our entropy produced. This statement doesn't require that the entropy change be positive for both the system and the surroundings, but only that the sum is positive. The increase in entropy principle dictates the direction in which any process can proceed. And that direction is the direction that causes entropy of the system plus the surroundings to increase. So we look at an example. We have 0.8 pounds of a metal bar initially at a temperature is removed from an oven and quenched by immersing it in a cooling tank containing 20 pounds of water at an initial temperature. Each substance can be modeled as incompressible. An appropriate constant specific heat value for the water is 1 BTU per pound degree Rankine, and an appropriate value for the metal is 0.1. Heat transfer from the tank contents can be neglected. We want to determine the final equilibrium temperature and the amount of entropy produced. So we have our energy balance. It tells me my change in internal energy is going to be equal to 0 because there's no kinetic, no potential, no heat transfer, no work. What this really means is the change in internal energy for the water plus the change in internal energy for the metal bar has to equal 0. We're going to use constant specific heats. We're going to get the mass of the water times the specific heat of the water times T final minus T initial of the water plus the mass of the metal times specific heat of the metal times T final minus T in the metal equals 0. So if we solve this for TF, we get if we insert some numbers, we have our 20 pounds of our metal times the ratio of our specific heats, which is 10, times 530 degrees Rankine, we're going to get our final temperature is 535 degrees Rankine. To figure out the entropy, if delta S is equal to the integral of Q plus sigma. So delta S is equal to delta S of the water plus delta S of the metal, which is equal to the mass of the water to specific heat of the water, is the natural log of TF plus the mass of the metal, specific heat of the metal, times the natural log. So sigma is equal to 20 times 10 BTU per pound degree Rankine times the natural log of 535 over 530 plus 0.8 . Overall, we produce 0.0864 BTUs per degree Rankine. So now we're actually going to introduce the entropy balance for open systems. It's an extensive property. It can also be transferred into and out of a system by mass transfer. So our entropy rate balance is the rate of entropy within the control volume is equal to the sum of any heat transfer that's occurring at the boundaries plus the entropy that is entering the system with our mass flow minus any entropy that is exiting the system with our mass flow plus the rate of entropy production within the system. We can also express it in terms of local properties, but we're not going to go over that. More importantly is what happens for a rate balance for steady state. If we remember, our mass and energy balances take the form of, well, what comes in is equal to what goes out for our mass, and we have our heat transfer rate minus our power plus the sum of what goes in with our mass flow in terms of enthalpy plus kinetic plus potential minus what goes out with our mass flow in terms of our enthalpy, kinetic, and potential. The same goes for our entropy balance. We'd have the sum of what's occurring at our heat transfers at our boundaries plus the sum of the entropy coming in minus the sum of the entropy going out plus whatever entropy is being produced. You have to solve these equations simultaneously with any relevant property relations. Also, I want to remind us again that while mass and energy are conserved, entropy is not conserved. Entropy is actually produced. So the rate at which entropy is transferred out must exceed the rate at which entropy enters, with the difference being the rate of entropy production. What happens if we have a one inlet, one outlet control volume? Then we have the sum of our heat transfer at our boundaries plus our change in entropy from our inlet to outlet plus our rate of entropy production. Or if we divide by mass, we have our specific entropy for the special case, when there is no entropy accompanying heat transfer, we have that our change in entropy is equal to the entropy produced within the system. If irreversibilities are present within the control volume, the entropy of a unit mass increases as it passes from the inlet to the outlet. In the limiting case in which there are no reversibilities present, the unit mass passes through the control volume with no change in its entropy, so it behaves isentropically. We're going to look at an example of steam entering a turbine with a pressure of 30 bar and a temperature of 400 degrees Celsius and a velocity of 160 meters per second. Saturated vapor at 100 degrees Celsius exits with a velocity of 100 meters per second. At steady state, the turbine develops work that's equal to 549 kilojoules per kilogram. Heat transfer between the turbine and its surroundings occurs at an average outer surface temperature of 350 Kelvin. We want to determine the rate at which entropy is produced, and yeah, that's it. We just want to figure out the rate at which entropy is produced. So first we have our mass balance, which just tells us that there's one inlet and one outlet, so there's only one mass flow rate. We do our energy balance. We have our heat transfer rate is equal to our work plus our change in enthalpy plus our change in kinetic energy, which is equal to the 540 kilojoules per kilogram that's given, plus our change in enthalpy, which I got by defining my states and looking them up in my tables. Plus my change in kinetic energy, so my heat transfer comes out to be minus 22.6 kilojoules per kilogram. And I do my entropy balance. I have 0 is equal to the sum of my heat transfer plus my mass flow rate times my change in specific entropy plus what's produced. So my entropy produced is equal to the heat transfer that occurs across the boundary plus my change in specific entropy, which is equal to minus 22.6 over 350 plus 7.3549 minus 6.9212. We produce 0.498 kilojoules per kilogram Kelvin in entropy. I'll do another quick problem where we have air entering a compressor operating at steady state at 15 psi and 80 degrees Fahrenheit, and it exits at 400 degrees Fahrenheit. There's no heat transfer and kinetic or potential energy changes. Assuming the ideal gas model for air, we want to determine the maximum theoretical pressure at the exit. So from our entropy balance, we have 0 is equal to the sum of Q over T plus M times S1 over S2. Let's reduce. So our entropy production per unit mass flow rate is equal to our change in entropy, which is equal to S02 minus S01 minus R times the natural log of P2 over P1. The min pressure occurs for no entropy production. So if I solve for my pressures, the natural log of my pressures is equal to S02 minus S01 over R. This is 1.64032. Solving for P2, you get P2 is equal to 77.35 pounds per inch squared. That's it for this lecture. And our next lecture will take a closer look at what you can do for some isentropic processes, particularly with ideal gases.